What if your AI could handle 1 million tokens of context without melting your GPU? That's exactly what DeepSeek version 4 just solved. Developers know this pain. As context windows grow larger, attention mechanisms become insanely expensive. More memory, more compute, more cost. This is called the quadratic wall, and it's one of the biggest bottlenecks in AI today. But DeepSeek spent the last year rebuilding the transformer architecture from the ground up to break that wall. Introducing the DeepSeek version 4 series, DeepSeek version 4 Pro with 1.6 trillion parameters and 49 billion activated, and DeepSeek version 4 Flash with 284 billion parameters and only 13 billion activated. These models are not just bigger, they are smarter, more stable, and massively more efficient, built to natively support 1 million token context windows. That means better agent workflows, massive document analysis, and truly long term reasoning. DeepSeek version 4 is making infinite context finally practical. And honestly, this changes everything. So, how does DeepSeek version 4 handle 1 million tokens of context without destroying your GPU budget? The answer is a massive architecture upgrade. Instead of relying on standard attention, DeepSeek version 4 uses something called hybrid attention. And this combines two specialized systems, CSA and HCA. Let's make this super simple. First, compressed sparse attention, CSA. Think of CSA like a smart library system. Imagine you're searching for one book in a library with millions of pages. You would not read every page, right? You would use index. That's exactly what CSA does. It compresses key value memory by 4 times and then uses something called the lightning indexer to find only the most relevant parts. Instead of checking everything, it selects only the top 512 or 1024 blocks for attention. Result: high precision retrieval with way less memory, fast, accurate, and efficient. Second, heavily compressed attention, HCA. Now imagine instead of searching for details, you just want the big picture. That's where HCA comes in. This one compresses memory by a massive 128 times, way more aggressive, but unlike CSA, it does not select top K. It attends to everything just in compressed form. This helps the model maintain the global understanding of the entire million token context. Basically, CSA finds the exact answer, HCA keeps the overall story. Together, perfect balance. But what about recent details? What if compression loses important context? DeepSeek solved that too using sliding window attention. With a window size of 128, this keeps the latest tokens fully uncompressed. So recent information stays sharp and crystal clear. They also use something called attention sinks, which helps dump unnecessary attention scores into special sync tokens, preventing instability that usually breaks long context models. So in simple words, CSA is equals to precision, HCA is efficiency, sliding windows is clarity, and attention 6 is stability. And that's how DeepSeek version 4 makes million token intelligence actually possible. Building a trillion parameter model is not just about making it bigger, it's about stopping it from completely crashing. And one of the biggest problems is training instability. Sometimes the signal inside deep models becomes too strong and it explodes. Other time it becomes too weak and disappears completely. This is the classical problem of exploding and vanishing gradient. And it gets way worse when you scale to trillion parameter models. DeepSeek version 4 solved this with something called Manifold-Constrained Hyper-Connections, or MHC. Let's simplify that. Traditional models use something called hyperconnections to manage residual streams across deep transformer layers. They help information flow, but at massive scale, they can become unstable and cause training crashes. So DeepSeek upgraded them. Here's the clever part. They mathematically constrained the residual mapping matrix inside something called the Birkhoff polytope. Sounds scary, but here's what it actually means. They force the signal transformation to stay controlled. They use the Sinkhorn-Knopp algorithm to normalize everything. So the signal never becomes too large or too small. Think of MHC like a super advanced signal repeater. Imagine sending a message through 60 plus floors of a building. Normally, the signal would weaken or overload, but MHC makes sure the signal stays perfectly balanced or start to finish. No explosion, no vanishing, just stable learning. This allows DeepSeek version 4 to train across 60 plus massive layers without losing stability or performance. In simple words, MHC makes trillion parameter training actually reliable and honestly That's one of the biggest breakthroughs in modern LLM engineering. Most people think AI efficiency is only about faster inference, but the real magic starts during training because efficiency is not just how a model thinks, it's also how it learns. And DeepSeek made two massive upgrades here: Muon Optimizer and FP4 Quantization. Let's break it down. Most models today use something called AdamW for training. It works, but a trillion parameter scale work is not enough. DeepSeek replaced it with Muon, and Mayan is much smarter. Instead of normal weight updates, it uses something called Newton-Schulz iterations to make updates more organized. Think of it like this. Imagine a team is trying to push a car. With bad coordination, everyone pushes in random direction. Lots of effort, less progress. Mayan makes sure everyone pushes in the best direction. Every update becomes more informative and more efficient. Result: much faster convergence. The model learns faster and fewer wasted steps. Next, FP4 quantization. Now let's talk memory. Big models are expensive because moving data is often slower than computing. DeepSeek solved this using FP4 quantization, also called MXFP4. Instead of storing weights in large precision formats, they compress them down to just 4 bits, especially for MOE expert weights and lightning indexer path. They massively reduce memory traffic during inference. Less data movement means faster response. It also speed up attention score calculation inside the lightning indexer. So not only is training faster, inference becomes faster too. In simple words, Mayan is equals to smarter learning, FP4 is equals to lighter memory. Together, DeepSeek becomes faster to train, faster to run, and far more efficient. And that's how next generation LLMs are built. 1.6 trillion parameter model is not just AI research, it's hardcore engineering. At this scale, even tiny inefficiencies become massive problems. So DeepSeek had to build something called the Mega-Kernel approach, where the biggest challenge is simple: balance the hardware perfectly. Let's break it down. First, the golden hardware ratio. When you train giant models, your GPU is constantly doing two things: computing and communicating. If communication is too slow, your expensive GPU just sit there waiting. That's wasted money. DeepSeek found a sweet spot called the golden hardware ratio, where compute and bandwidth perfectly overlap. The rule was C divided by B must be less than equal to 2D. Sounds technical, but here's the simple version. For every 1 GB per second of bandwidth, you can hide around 6.1 teraflops per second of compute, meaning the GPUs stay busy instead of waiting. Maximum efficiency. Second, tile length plus Z3 solver. Writing kernels for trillion scale models is incredibly complex. One indexing mistake and performance collapse. So DeepSeek used TileLang, a special programming language built for fused kernels. But here's the crazy part. It works with the Z3 solver, which is basically math powered code verification. Before the code even runs, Z3 checks if tensor indexing is mathematically optimal, not probably correct, provably correct. That saves huge amounts of debugging time. Third, deterministic training. Now imagine debugging a model across thousands of GPUs. Absolute nightmare. If results change every run, you can't fix anything. That's why DeepSeek focused on bitwise reproducibility, meaning every training step can be replicated perfect. Normally, GPUs use something called atomic add, but it creates randomness. DeepSeek avoided that. Instead, they use separate accumulation buffers for each SM and then performed one final determination summation. Result: every run is identical. Perfect debugging, reliably training. So, in simple words, golden ration is full GPU efficiency. Tile lang plus Z3 is mathematically perfect kernels. Determinist training is reproducible result. This is an invisible engineering that makes trillion parameter AI possible. Because at this scale, software is only half the battle. Training a trillion parameter MOE model is like trying to control a rocket during launch. One small mistake and suddenly everything explodes. In AI training, this disaster is called the loss spike. Your training suddenly becomes unstable, performance crashes, and sometimes you have to restart everything. DeepSeek built two powerful safeguards to stop this: anticipatory routing and SwiGLU clamping. Let's simplify both. In MOE models, routing is everything. It decides which experts gets activated for each token. But here's the problem. If the backbone model makes a bad update, routing gets worse. Then bad routing causes even worse update. And suddenly you enter a vicious cycle. Everything spirals downward. DeepSeek solved this with anticipatory routing. Instead of updating routing at the same time, the model actually looks ahead by caching routing decision from previous step. It separates backbone updates from routing updates. This prevents bad updates from instantly breaking the routing logic. Think of it like driving with GPS. Instead of reacting too late, the model plans ahead before taking the next turn. much safer, much more stable. Next, SwiGLU clamping. Now let's talk activation. Deep models often use SwiGLU, which is powerful, but sometimes it creates extreme outliers. Some values become too large, gradient becomes unstable, and training gets messy. DeepSeek fixed this with something simple, clamping. They kept the linear values inside SwiGLU to a safe range of -10 to +10. That's it. Simple, but incredibly effective. It removes extreme outliers and keeps gradient smooth. Less chaos, more stability. So, in simple words, anticipatory routing is smarter expert selection. SwiGLU clamping is smoother gradients. Together, they protect the model from catastrophic loss spikes and make trillion scale training more reliable. Training the base model is only half the story, because after learning from 33 trillion tokens, the real transformation begins. This is where DeepSeek version 4 goes from just a powerful model to a true specialist agent, and this happens through post training. Let's break it down. On policy distillation, OPD, most companies combine expert models using something simple called weight merge. Sounds easy, but it often makes performance worse. Why? Because mixing weights can destroy precision. DeepSeek uses something smarter, on policy distillation or OPD. Instead of merging weights, the student model learns directly from the outputs of multiple expert teachers. Think of it like this. Instead of copying the teacher's notebook, the student learns from how they actually solve problems. One teacher for coding, one for math, one for reasoning, and the final model learns from all of them without losing their expertise. Result, one unified model with specialist level skills. Second, reasoning modes. Not every task needs maximum brain power. Sometimes you want speed, sometimes you want deep reasoning. So DeepSeek added multiple thinking mode. Non-think mode, fast responses with 8K context, perfect for quick answers. High mode, deep logical analysis with 128K context for serious reasoning tasks. Max mode, absolute maximum intelligence with 384,000 tokens. This pushes the model to its logical limits. Basically, you choose how hard the model should think. Third, interleaved thinking. For agent workflows, reasoning across multiple steps is critical. So DeepSeek introduced interleaved thinking. This preserves the full reasoning history across multiple tool calls. The model remembers how it was thinking, but in normal chat, that history gets clear. To keep the context window fast and efficient, smart memory management. Fourth, quick instruction. Using special tokens like action and query, the model can instantly decide whether it should search the web, call the tool, or take another action. And here's the best part, it reuses the existing KV cache, which means no repeated pre-filling and much more lower latency. Faster time to first token, faster responses, better user experience. So, in simple words, OPD is a specialist transfer, reasoning model is adjustable intelligence, interleaved thinking is better agents, and quick instruction is lower latency. And that's how DeepSeek becomes not just a model but an intelligent system. So, after all these upgrades, the big question is, did DeepSeek version 4 actually deliver? Short answer, absolutely. And the numbers are honestly insane. Let's compare. First, inference efficiency at 1 million tokens. This is where DeepSeek version 4 becomes scary good. Compared to version 3.2, version 4 needs only 27% of the flops and just 10% of the KV cache. That means dramatically less compute and far less GPU memory. Already huge. But then comes version 4 Flash. This only needs only 10% of the flops and just 7% of the KV cache. That's a 13.7 times KV cache reduction. For a million token inference, this is not optimization. This is a complete architecture leap. Second, knowledge plus reasoning performance. Efficiency is useless if the model becomes dumb. But DeepSeek did not sacrifice intelligence. On simple QA, DeepSeek scored 57.9%, while GLM 5.1 scored only 38.1%. That's a massive jump on humanity's last exam. DeepSeek reached 37.7%, showing strong high level reasoning. And for competitive programming, this gets crazy. On code forces, DeepSeek achieved a 3206 rating, putting it in the top tier of human coders. Yes, human level elite coding performance. Third, real R&D coding. Benchmarks are great, but real world engineering matters more. For internal R&D coding tasks, DeepSeek version 4 Pro solved 67% of tasks successfully. That's put it close to Claude Opus 4.6, which scored 80%. With its advanced thinking mode, this is a serious competition. Final conclusion, DeepSeek version 4 isn't just another LLM, it's a new foundation for efficient scaling. It proves that million token intelligence does not have to mean $1 million infrastructure. By breaking the efficiency barrier, DeepSeek shifted the real bottleneck from hardware back to human creativity. The future of AI is no longer limited by memory, it's limited only by the complexity of the questions we dare to ask. And honestly, that's where things get exciting.